Okay, so now we talked about filters, and last time we talked about the insertion loss, all right, when we ended by defining the insertion loss and the ratio primarily, so it's called the insertion loss ratio, because we said we are going to define, develop designs of filters using this approach only, the insertion loss method. So using the insertion loss method, there is an important ratio, and then the load is Z0, which is the reference impedance. And then you have here your ZS and your voltage generator. And if this is gamma sub I, and that is also defined in terms of Z0, all right, then, and initially, obviously, we are going to consider in our designs that ZS is going to be equal to Z0. So we define this gamma in as Z in minus Z0 over Z in plus Z0, okay? And then the insertion loss ratio is nothing else but the 1 over 1 minus magnitude of gamma input square, okay? That's where we ended up. And there is one more entity from this. You will see it, so I will need to give you that. The other entity you're going to see is insertion loss as a logarithm in dB, so as 10 logarithm of this ratio. And you're gonna see it in dBs. And I have to tell you, that's what everybody's using. So when you start in filter design and people are communicating about how a filter performs, we'll always talk about insertion loss in dBs. So we need to keep that in mind. Now, before we continue, we are gonna make an important observation about how this gamma sub I, the reflection coefficient, in terms of the function, how does it look? So obviously we're gonna go back to fundamentals, and we can rewrite gamma sub I as the normalized input impedance. Okay, I can even put input here so you know. Design frequencies at design filters at one particular frequency, and that is called the design frequency, where we want the filter to perform the best, all right? Away from that frequency, your gamma sub I is gonna be a function of omega. Now, please let me know if you don't hear me well. Do you hear me well? Because I got a note that the connection is not that great. I don't know what that means, but can you hear me?
Yes.
Yeah, we can hear you.
Okay, perfect. Okay, that's great. So, of course, at the given frequency, this is going to be a number. But as you go away from that frequency, because you remember we talked about bandwidth, all right? So you don't only design a circuit at one frequency of interest, and usually that's your design frequency, but you take into consideration how this is going to operate away from that frequency, because every system has a bandwidth, which means that while we design it in one frequency, we operate it over a frequency range. So how it operates over that frequency range is extremely important. And many times we even worry about how the system performs outside of that frequency range for obvious reasons. So away from the design frequency, your gamma sub I is going to be a function of frequency. And now when we have it in this insertion loss ratio as a magnitude squared, what is a magnitude square of that deflection coefficient is gamma sub I times gamma sub I complex conjugate. So practically, that means if I were to write gamma sub I as a function of omega, then this is going to be gamma sub I omega times gamma sub I complex conjugate of omega. Okay. Now, for a moment, let us go back and look at Z. And so practically, if we take, I will do one more step. If we go from look at 1 and then we look at 2, what then we get is gamma sub I of omega, and that magnitude square is going to be Z in, which is now a function of omega, all right, minus normalized, minus 1. So practically is the normalized. And then Z in of omega plus 1 times Z in complex conjugate of omega minus 1, Z in complex conjugate of omega plus 1. That's what you have. So all of the complex conjugate at the end goes to the input impedance. Okay. So now let's write the input impedance, which is a function of omega, as a function that has a real part, R in omega, plus an imaginary part, X in omega. All right, and if this is normalized, those will be normalized, obviously. So in this case, Z in complex conjugate of omega will be what? R in of omega minus J X in of omega. Okay, and this is, say, 3 and 4. Do you agree so far?
Yes, ma'am.
Okay. Now, when we match a, and let me add here one page because we are not ready. Now, when let me go back to the system. We have a system here, all right, and that system has a load Z naught, and that's our filter. And then here, we have the input. And then here, let's assume for a moment that Z sub S is not Z naught, because in the Z naught case, what I'm gonna state is gonna be obvious, but let's assume that this is ZS, okay? Now, in case where ZS is not a real load, or R naught, obviously, but it's an imaginary, a complex load, in that case, we try in our best, for our best performance of our filter, to get into the filter the maximum available power from the source. So to be able to get the maximum available power from the source, this needs to be how much? What do you think?
ZS star?
Complex
Exactly.
conjugate, yeah.
Exactly. It has to be the complex conjugate. And in that particular case, obviously the reactance of Z in cancels out the reactance of ZS, and the source delivers to the filter the maximum power. So this is going to be maximum available. Okay. Now, the maximum available, let's go back to, I wanted to tell you, therefore, that even if we have assumed that what enters, the real power that enters into our filter is the maximum that can become available by the source. And therefore, we don't have to worry if we go and assume that ZS equals Z naught, because everything that is going to come out of this is going to be true for any other case. Okay, that's why I made that statement. So now let's go back to where we have assumed, our Z sub S is going to be. Therefore, the power that is going to be delivered to the filter is going to be, in this particular case, the maximum available is going to be a real power. All right. And as a matter of fact, it's going to be the PLR. This is what is going to go into the filter, because it's going to be the PI 1 minus gamma I magnitude square. All right. And when we took the ratio of the PI, in fact, I should probably call that something different. One moment. Let's call that still maximum available. Okay. When we took the PI over PI maximum available, then that gave us 1 over 1 minus gamma I squared, and that is our PLR. Okay. Now, these powers are real. And therefore, what we have is that PLR, obviously, is the maximum power that goes inside. This also, all of them. Let me, in fact, this one plus this one plus the IMA, they will all be real, okay? And if for a moment we assume that our design frequency is 0, then you're going to find out that P, each one of those powers, all right, including PLR, PI, or PI maximum available, all of these will be even functions of the frequency. So if I were to go and replace our frequency with a negative frequency, and negative frequencies are important, as we said, when you do calculations and when you do modeling and analytical things, or when you look into Fourier transforms. Because in reality, there is no negative frequency. But when we go and look into Fourier transforms, or we look at also at functions like mixing and other things, negative frequencies that eventually may become important, may be in the negative domain, but if you start doing manipulations with frequency, they eventually can show up in the positive domain of frequency. So in any case, when you see here, you may say, well, what does a negative frequency mean? And I will tell you nothing much. The only thing is, in reality, in the real world, but in the Fourier domain, it has meaning, all right? And in the frequency domain, a negative frequency has meaning, but the frequency domain, the way we introduced it, is a mathematical domain. Even if a frequency is also a real entity, and when we say we have 5 gigahertz, we mean positive 5G. We don't mean negative 5G, all right? So the Fourier domain is an analytical mathematical domain. Frequencies are real entities in the time domain. But when we start talking about how a function behaves as a function of frequency, that you may see what I have here. Why is this important for us? This is important because if this is true, then what you also find out are 2 things. The way we explained the Z input and Z output, if this is true, then practically I have that gamma eventually of I omega I omega times gamma I complex conjugate omega is the same with the entity where I could replace every omega with minus omega. And then if you do that, you are going to find, if you take this into consideration, and also you take how gamma sub I looks like, all right? So if you take that plus the fact that gamma sub I of omega is really what? R sub A, R of omega input, R input of omega, plus J X input of omega, all of this normalized, minus 1, divided by R input of omega, plus J X input of omega, plus 1. Okay, so that's what we have so far. We have this relationship, and we have this. And if you use the two, and there is an analysis in the book, but I will just summarize it here. In fact, it is, I have analyzed it also in my notes. So, but I will then I will skip this analysis that you can find in my notes, and I will tell you the following. That from here, you can write that gamma sub I of omega magnitude square is going to be the following. R sub in minus 1 square plus X sub in normalized square divided by R sub n plus 1 square plus X sub n square. So that's what you have. And then it's very interesting to show that practically this is written in this form as a function of omega square divided by the same function plus another function. Okay, so that's what we found, which is very interesting because what this is telling us, also the details are in my notes, but the final outcome is going to be very important. It tells us that if we take this expression and we plug it into the insertion loss ratio, which is 1 over 1 minus gamma sub I of omega square, what you find is that this is equal to 1 plus a simple ratio of these two functions. Now, you may say, you look at that and say, who in the world would do all of this to be able to design a filter, and what does this really do? You need to remember that people were designing filters when computers were not available. And as I have told you many times before, those designs have remained in time. They have not been altered. And why is that? Because they allowed people to develop design methodologies. A computer cannot help you develop a design methodology unless you use data analysis. You throw a million of different analytical solutions to circuits, then the computer finds a relationship by observing these million possible performances of a million combinations of RLC circuits, finds a relationship between the performance and the specific of the elements, and then gives you that, all right? Like, for example, they did this very recently with the COVID-19, and they do it for other problems, but where you don't know the relationship between an output function and the input parameters. Now, if you have that computer, you can do it, and Now, MATLAB can do designs, but MATLAB is using the formulas that I'm describing to you. MATLAB is not doing another design, just using the same formulas. At the same time, when MATLAB and other things or other circuit routine software was not available, these people were doing the designs with tables. And so they developed that formula because practically from here, they were able to do two different interesting designs. One, therefore, from this formulation, I'll rewrite it here because we are going to start with that. From this formulation, which is PLR equal to 1 plus a function of omega squared divided by another function of omega squared, so you can write it in this form, people were able to create two separate, very interesting designs. One was called the maximally flat filter design, and the other was called the Chebyshev, or equal ripple or Chebyshev design. Obviously, each one of them speaks about what the filters will do. In one case, the filter performance for that insertion loss ratio, all right, it's when omega is 0, it starts at 1, the maximally flat, and it goes, as it says, it's flat and goes up. The lowest value, it shows the maximum power that goes through the filter and is delivered eventually to the load. All right, so if you remember how we got PLR? We got that from P input divided by what was reflected. In fact, what went through, excuse me. When this is 1, that means the maximum available by the source is going through, okay? We don't use maximum, there are too many. So the P sub I is the maximum available by the source. Practically what is delivered and what goes there is the same, 1. So that's where the best performance of the filter, okay, erase everything, is here. And then it goes well up to some number. And the way we plot this is the following. We make the agreement that this one is not going to be just a simple frequency, it's going to be omega over omega sub c. And this is the PLR. And an important point here is that where this ratio is 1. And all right, so that is the first. And for the maximally flat also, what using this form for the insertion loss ratio, then for the maximally flat, this one becomes 1 plus, and then K, which is a constant, omega over omega sub c, 2 to the n. So that is the form simplified, all right? So they simplified, and those gave all the family of all of the maximally flat filters. Okay, that was one. Then they developed this other, what they call the equal ripple or Chebyshev design. And for this particular case, PLR equals 1 again, a constant k squared, and then instead of the ratio omega over omega c to the 2n, they give a Chebyshev polynomial to the second power. The order of the polynomial is n, and then it gives this ratio. Now, why did they go from the simple omega over omega c to something that is more complex and has a Chebyshev polynomial? And you can go and check what if you want to see what the Chebyshev polynomials are, kind of interesting. They have both an oscillatory performance and also a
Dr. Katehi,
monotonic performance. Yes.
is that omega C or L?
Where?
Our equal ripple or Chebyshev design, RLR equals 1 plus k squared plus tn squared times omega over omega. Is it C or L?
C.
Okay.
So, and that's the order, nth order here. All right. Now, as I said, the Chebyshev polynomials have two interesting properties. They are both oscillatory in form and also monotonic. And so this was selected. So instead of going flat, the filter will do this oscillation and then go up. Now, and that it's better done in my notes, but this is where omega over omega c equals 1. And this is the 1 plus k squared. Now, why did they bother to go from the easier one to the more difficult one? Because they found that for a filter that has the same more or less number of elements, if the design has been done to really create that PLR, to create that PLR that has the Chebyshev polynomial, then the monotonic behavior is more steep than it is in the other filter. So if I were to take the two and overlap them, what would I find? I would find that for the same order filter, then I will get something like this for the Chebyshev. So if you now were to invert the way we have plotted the P function, all right, so practically in the filters, you're not going to see the P, practically you're going to see the inverse of that. So you're going to see somehow the same, but upside down, the same performance. So for maximally flat, they will look like this, all right? And for the equal ripple, if this was again the 1 point, no. That was omega over omega c to be 1. Then the other one would look like this. And maybe with more drastic performance, improvement in performance. So if I were to do that, it would look more like that, okay? So we have these two designs. How to, now, if you have any questions, I will stop to hear any questions you may have, and then I will proceed. Do you have any questions so far?
I do.
Okay.
What is the y-axis in this plot?
Why the x direction you mean?
The y-axis.
The y-axis here is what goes through. So practically, it's going to be the inverse of the PLR. And usually we give it in dBs, all right? So this is going to be, if I were to in the way we plot it. Is one, if they're both in logarithms, so it's just like one is the reflection of the other, practically. Is that clear?
Yeah.
Okay. Any other questions? All right.
And PLR is what's delivered to the filter, correct?
PLR is the, this one is the insertion loss ratio, which is this, you see? But when, and then if you plot that, this, I mean, it's not wrong. If you choose to plot that, it's gonna, your curves will look like this. If you choose to plot the other one, they will look like that.
So the insertion loss ratio is the power delivered to the filter over the maximum possible power delivered to the filter.
Yeah, usually what happens with this, no, the insertion loss ratio is the maximum delivered available by the source divided by the maximum delivered to the filter.
Okay, that makes sense.
Okay, this one. The other one is the inverse of this. So if you follow the power loss ratio, everything starts at 1, which is like in dBs will be 0 and up. All right. So everything from 0 positive. If you look at the other one, it's going to be from 0 negative. But it's a way of looking at things. Usually, the reason I'm going down here is because this is what most people have. But feel comfortable with either one. It's not wrong if you choose one over the other.
And the design, I guess you pick based on like, does the frequency go below WC? If it goes below
No,
WC,
let me, don't make any conclusions about that because this is the next I'm going to discuss.
Okay.
Okay, so now let's go to the design. The design is a whole like recipe, all right, here. It's not like obvious how to go from where we start to the next. So we will have to, I will have to introduce it to you. Now, obviously, the people who developed that design, they had the whole reason of doing it, but we're not going to go through that. Nobody learns it, nobody remembers it, and it's not important on how they got into what I'm going to show you. But you need to remember what I'm going to show you right now. So the fundamental thing in the design, so design process, is to do the following. Start with what we call a prototype design. So start with the design of what we call the prototype, and I will define it. Now, next. What is a prototype? Prototype. Prototype is a filter. It's kind of a generic thing. It's not real. It's part of the design. But we call it a prototype to understand because by telling you a prototype, you understand all of the properties. First of all, the prototype is a low pass. It's a low pass circuit. 2. In the prototype, we assume that omega c is 1 hertz. And we call omega c the cutoff, not 1 hertz, but has 2 pi. All right, let me just put that. But omega c, let me be more accurate, is 2 pi fc. and this is 1. And it's radians per second, but you know, the units are not important. If you were to be accurate, I will say rads per sec. But I will not worry about the units in the prototype. So 1. Then we assume that the prototype is terminated, that filter, that circuit is terminated at a load, which is 1. I will put here omega as ohm, but as I said, I would like to show, to put some reality to this and put the units the right way, but the units are not important because you will see later why they're not important. Practically, they're like numbers. And then the fourth thing is that we assume that R sub S, which is the generator's real part, is 1. I'll put here ohms, not important. And just so you remember, resistors, equivalent of resistors, omega C is a kind of a frequency, but all part of a prototype. And this prototype in general, other than remembering the entities, what entities we have there, units are not important because units will come out later. All right, so then after we design, how then I will sketch out the process. So we start, somebody tells you, I want you to design a filter that has the following specs. So you start with the filter specs. And the specifications, you will see when I solve an example, the specs will be, I want a filter that is low pass, band pass, whatever, one of these. I want its cutoff frequency to be that, or I want to have a rejection of this much, so many, you know, at this frequency above your cutoff. That possible. And they may tell you that I also want to have a particular load at the end. They may. Usually that's the least important because almost 99% of the time we assume that we have 50 ohms on both sides. But the most important will be specifying omega C or specifying the rejection either at omega C or somewhere else, specifying the frequency of your design, specifying the way you want your rejections to be. So how steep the skirt is gonna be. All right, so these are the specs. Then from the specs, you go and design the low pass prototype. So you design the prototype. After you design, always the prototype is low pass. Even if they tell you that you want a band pass filter, you still are gonna start with a low pass. So you design the prototype and then you go to a number of transformations, which we're gonna do next week. There are a number of them. The easiest is, so I'll put here transformations. The easiest ones is frequency transformation, because you remember, you have defined in the prototype of omega C to be 1, but in the real filter it's gonna be something else. Then, so you have to do a frequency transformation. Then you will have to have an impedance transformation, because in the prototype, your impedance in 1 is 1, but in reality, it is something different. And then we have a transformations that we are gonna cover that will go from low pass to band pass, low pass to high pass, low pass to band stop, whatever else, all right? Because you start with a low pass in the prototype. So then you have all kinds of additional transformations, and they have different names. We'll see a number of them. And after you do that, you go through all of the transformations here. Then you have produced an RLC, but RLC complicated, all right? Because you're not gonna have only one R, one L, and one C, as you see, depending on how your filter wants to be, you may have many stages. But then it's going to be a multi-stage RLC. And then after you have that, now you want to go and realize it. So you have to go through realization, which means what? If my frequency is high and I'm telling you that we are working with microstrip, you will have to realize all of the R, L, and C using microstrip or a CMOS fabrication. I may tell you that I am on gallium arsenide and I'm working with coplanar waveguide. We're not going to do it for this class. But if you are an engineer out there, they will come and tell you, you know, the whole layout in all of our circuit is a coplanar waveguide layout. You go and design this filter, it has to be on coplanar waveguide. So this is the last part you do in the realization. And then you have in the realization to consider all kinds of different things as we've seen. The passives. How many parasitics do I have? Do I have parasitics in my passives? If, for example, I want to realize all of my inductors, instead of sections of lines, I want to have a spiral inductor, and my capacitors with MIM capacitors, and my resistors with MIM resistors. Then what are my passives? Because if I forget about the passives, then I design something that is going to have Okay, we have a few more minutes, and I would like then to start an example, which I'm going to then continue with next time. So let me do one more page here. Any questions so far? Okay, so the example, I want to develop, I'm telling you now, I'm giving you all of the specifics. I want to develop a filter and I want to be maximally flat because I like that it has this kind of smooth. There are applications where I want it to be smooth at my center, at the bandwidth that it has. So I want the maximally flat. And then I want my FC to be 10 gigahertz, meaning that I would like really the pass band for this to be below 10 gigahertz. And I want it to be a low pass filter, obviously. In this case, I did not speak about center frequency, so low pass filter. I want to have a source impedance of 50 ohms and a load impedance of 50 ohms. And I would like to have a rejection of 20 dBs at twice the cutoff frequency. So at 2 omega C. All right, and then I want to first design it. So first design. 2, find the bandwidth. That's a real, for example, that's what a designer will have to do. And of course the Q. And then I don't know what else you may want, all kinds of other things you may want to find. But we're going to start with this. So this is the most important in what I'm going to select for how I'm going to go about the design. This one. Okay. So now I'm going to this that I will move up. These are tables that have been around and have been of Poser's book everywhere where you have, these are the tables that have been used. And what do they show? Every line shows a different n number. So the n is the number of stages. And in fact, n minus 1. So when you see n2, practically it's going to be one stage, 2 reactive components. All right. And 3, you go to 3 stages and so forth. I mean, 3 reactive components and so forth. So I want here my omega over omega c minus 1. This is what they plot here. Is so it's along this line. All right. So omega over omega c minus 1. That's what is plotted here. And then I want N2. So my omega is above in this particular case. Above 1, my omega is twice as omega c, obviously. So practically, that's where I'm looking at my rejection. So my rejection, it has to happen here. And what did I say? That I want my rejection to be better than 20 dBs. Now, for this example, this is very close, obviously, to n equal 3. For some other cases, if you are so picky about the 20 dB rejection at that point, you may want to go to n equal 4. But if that is not very critical, then I would stop with n equals 3. And then, in fact, in my notes, I put a different n. It does not matter anymore. But I mean, the notes I followed, it's just for a different. I want minus 15 dBs instead of 20. Let's assume. Somebody has a question?
Yes, why you choose y over yc minus 1 equal to 1?
That's where the 2, you see the 2 omega c? I want 2 omega. I want to have 15 dBs rejection at frequency omega, which is 2 omega c. So if omega is 2 omega c, then omega over omega c minus 1 is going to be 1. You see that?
Yes, thank you.
Okay. So now let's assume that I want 15 dBs. So this is my line. My line here is going to be this one, or a little higher. So I'm choosing this point. I'm choosing this point. Okay. Copy, whatever. There. That tells me that I have n equals 2. Okay. What does that mean? Now I have to go to the lower, this table, and I'm looking for n equals 2. And then what does that really mean? There are 2, and you will see that from the book. I suggest also that you don't only look my notes. My notes is like to help you understand what the book gives, all right? I have given also sections of the book that you need to read. From here, and I will stop it here because we're going close to 2:30, you're gonna see that I am getting these values. And also that I have 2 selections to make. Either if this is my resistor of my source, then I have a selection either to start with the capacitor immediately and go like that, or I have a selection to start with an inductor and go inductor capacitor then. The idea is that if I have a voltage source, I'm always starting with a capacitor. If I have a current source and then a resistor parallel to it, then I'm always starting with an inductor. All right? So with this, I will continue next time. But I wanted to tell you, we are, of course, these processes are not, I mean, these design processes, we cannot finish in one lecture. We are going to continue with that until the next week. And obviously that thing is not gonna be on your exam, but I would like anything that we had before that, before today, I would like you to review for your exam on Wednesday. So with this, we are going to finish today, continue on Monday, but Sunday from 3 to 5, we are going to have, we are going to solve problems to prepare for the exam. And today, on my office hours from 3 to 5, I will do some help, all right, for the last homework you have to turn on Sunday. Any questions?
Will the notes for that office hour be posted? I don't know if I'll be able to make it.
Today?
Yeah.
You know, usually if they are well organized notes, yes, otherwise no.
Okay, thank you.
I mean, I'm sorry, but I'm not going to provide a solution, all right? So I'm going to solve around the problem to help students solve it. That's what means help. So usually I have not prepared those.
Okay.
But ask one of your colleagues to give you his or her notes, you know, from your team.
And sorry, did you say you're doing that on Sunday?
Sunday will be different. I will have the notes for Sunday available. I'm talking about today.
Oh, so today is
the
the
office hours.
So today is the homework help for homework 5, and then Sunday is the exam review?
Professor, you are muted.
Can anybody hear me?
Yeah, we can hear you.
Can you hear me?
Now, yes.
Okay, perfect. I am sorry. The other one, I don't know, it just kicked me out of the Zoom, but that's all right. I have. Okay, so what I was gonna say is that today I'm gonna provide directions to help with homework 14, 14, the last homework you have to turn in this Sunday. Those notes I'm not going to have available because I have not prepared anything, and I'm going to do it right there at this, trying to ask the students and see what kind of questions they have. Sundays, however, I will put on the web. Okay. Is that the question? Somebody asked me, I believe that.
Yes, that answers my question. Thank you.
Okay. Okay, so I will see you at 3.